As a Cal 3 student, you may be taught about the transformation between Cartesian coordinates and spherical coordinates in a three-dimensional space. But early on when you learn about this, you're often told to just remember this fact without really knowing why. But actually when you later learn about the Jacobian matrices, you know how to show this fact yourself, and it's often left as an exercise for the students. So let's try to look at this problem now. Evaluate the appropriate determinant to show that the Jacobian of the transformation from spherical coordinates to Cartesian coordinates is rho squared sine phi. So first of all, we already know how to represent Cartesian variables in terms of spherical variables. So first of all, we have x is equal to rho sine theta cosine phi, and y is equal to rho sine theta sine phi, and z is equals to rho cosine theta. So with these variables in mind, we could now compute the Jacobian matrix. So how do we compute the Jacobian matrix? It's rather easy because we already have these three variables. So for the first row, it should be the partial of x with respect to the partial of rho, and then we have partial of x with respect to the partial of theta, partial of x with respect to the partial of phi, and then for the two coming rows, it will be the same logic. It would be something like this. So we have to know each of these partial derivatives. So let's try to compute them one by one. So first of all, we have the partial of x with respect to the partial of rho. So if we differentiate with respect to rho, it would just be sine theta cosine phi, because it will be the coefficient of rho. So the first item would be sine theta cosine phi. The second item would be respect to theta. So it would be the rho cosine phi, and then we differentiate respect to theta, so it will be cosine theta. So for the third item with respect to phi, so it will be rho sine theta, and then differentiate cosine phi, so it will be minus sine phi. For the second row, it will be sine theta sine phi with respect to theta, so it will be rho cosine theta sine phi with respect to phi, so it will be rho sine theta cosine phi. And for the third row, the first item would be cosine theta with respect to rho. The second item would be negative rho sine theta. Because we don't have phi, So the last one would be 0. And then we try to Laplace expand this, so it will be these four. So it will be sine theta cosine phi, and then the determinant of these four would be negative. The negative cancels out, so it will be phi. It will be rho squared sine squared theta cosine phi. And for the second term, rho cosine phi cosine theta, then determinant of these four would be negative rho sine theta cosine phi cosine theta. And then for the last term, it will be the determinant of these four, so plus minus rho sine theta sine phi, and then be minus rho sine squared theta sine phi minus rho cosine squared theta sine phi. And then let's try to further simplify this. So this will be equal to rho squared sine cube theta cosine squared phi, and then the second term is plus rho squared sine theta cosine squared phi cosine squared theta. And then for the third term, we have rho sine theta sine phi, and then we could draw out the negative rho sine phi as a common factor. And it would just leave us with sine squared theta plus cosine squared theta. So this would just be 1, because sine squared theta plus cosine squared theta equals 1. So we managed to simplify the third term a bit. So let's copy the first two terms. And the third term would be negative and negative makes plus, and then we have rho squared sine theta sine squared theta sine squared phi. And then if you notice, we again have some common factors in the last two terms, which is rho squared sine theta. So let's try to draw that out as a common factor again. The common factor is rho squared sine theta. And then cosine squared phi cosine squared theta plus sine squared phi. Actually, it would be better because we can't do anything with this. But if you notice, it's actually better if we consider the common terms, the common factors of the first two terms, because they actually have more in common. They have cosine squared phi in common. So let's draw rho squared sine theta cosine squared phi as the common factor. So we have rho squared sine theta cosine squared phi, and then that leaves us with sine squared theta plus cosine squared theta. So that gives us 1 again. And then finally, we have rho squared sine theta cosine squared phi plus rho squared sine theta sine squared phi. So again, we draw out the common factors. It'd be rho squared sine theta would be the common factors, and that leaves us with rho cosine squared phi plus sine squared phi. So again, that gives us 1. So the Jacobian is rho squared sine theta, which is what we needed to prove that this is the Jacobian. QED.